what we will do is we will talk about material selection and some of the key things. How do we decide something called these parameters, these materials indices? So I gave you a little bit of hint in for a very simple condition where there is a tie dot. So I will probably do that a little bit today. But before that, there are a few more material charts which I would like to finish. So one of the things is strength at high temperature. This is a very important thing because what happens is at high temperature, the material softens. The material softens because of recrystallization, and this softening can be significant. Material softens. The softening can be significant. It can be up to 50% reduction. So what it means is that it can deform very easily. So there can be plastic deformation easily. And the other thing that can happen is something called high temperature creep. High temperature creep, which basically means even if I do not change the load remains the same, there will be deformation and deflection. So how do we address this is that we need something which doesn't really soften at high temperatures. So some of the things which I would like which is outstanding is nickel superalloys. They're called Inconel. These materials are used in high temperature components of engine. The low temperature you can use titanium, but at high temperature you're bound to use some special materials, and these are called nickel superalloys, and they have very good high temperature performance. So Inconel can be one material, and wherever there is no tension or bending, ceramic can also be a very good choice. So either I have to go with nickel superalloys or ceramics if you really want strength at high temperature, right? Otherwise, if you would see that operating temperatures are different, so you see that 4 to 500 degrees centigrade is where I can use FRPs. So any high temperature FRP is not there. I can use alloys, but then alloys also, steel alloys, I cannot do more than 1000 degrees centigrade. Above 1000 degrees centigrade, it would be very difficult to do because it will start undergoing a lot of softening. Okay. So for higher temperatures, there are certain alloys and ceramics which you will have to use, primarily nickel superalloys.
Sir, are you sharing your screen, sir?
I thought so. My screen is visible to all the participants, right?
Yes, sir.
Yeah.
Yes, sir.
Yes, sir. It's visible.
Good. Because I'm actually having another computer to see what you guys see. So it shows me the screen as well. So the other important aspect would be relative cost, and cost is very important, mind you, because lot of your design decisions will be a function of relative cost. So this is very important. So I would basically have a ceiling that I want this property, and anything that meets that performance index, I will choose something that that is cheapest for me. Right. So we'll have to make the call, the final selection. Once we identify a number of materials which actually help, I will identify some of the things. I'll basically have a list of possible candidates, but the ones which I will select have to be cost effective. I think that's so. It should meet the functionality at the lowest cost is what you do a part of design. So if you see, the costs of relative cost, if you see per unit volume, ceramics and CFRP, those are very expensive. So the CFRP is right here, carbon fibers, they're very expensive. Although they have very good strength, and modulus also is reasonably high. So you get reasonable amount of modulus and strength, but they come for a price. And ceramics also are very expensive. And the other expensive item is tungsten alloys. So tungsten alloys are very, very strong, but unless and until there is a tungsten is exceptionally hard, you can use it for high temperature applications, but tungsten is so expensive that you have to pick and choose tungsten for a very niche application where you can justify the cost. So the expensive materials would be CFRP. Sorry, let me go back. CFRP. So that is carbon fiber reinforced plastic. These are expensive. Reinforced plastic, CFRP, and ceramics. And then engineering ceramics are reasonably expensive. So unless and until there is a requirement, we don't go with expensive ceramics. But ceramics are used where there are really high temperature applications. So ceramics you will have to use, but then you have to understand that they will not take a lot of tension and bending. These are brittle, right? So you have to understand where to use ceramics. And then the other cost thing is tungsten alloys are very expensive. And also aluminum alloys, titanium alloys, high strength aluminum titanium alloys. Those are also very expensive, because those actually go only for, if you see, titanium alloys are with CFRP, same price. Nickel super alloys are also reasonably expensive. So these are expensive materials. Aluminum alloys, aluminum, titanium, sorry. Aluminum, titanium, and nickel super alloys. Sorry, that's like jumping all over the place. Aluminum, titanium, and nickel. These super alloys are expensive. Aluminum, titanium, and nickel. And these are primarily find application in aerospace. So where you can actually justify the cost. Aerospace and defense are two areas where you can justify the cost. But then if you're making it for mass production, aluminum, titanium, and nickel have to be used with caution. There has to be a functional requirement where you justify the cost. So these are expensive. Carbon fiber is expensive, and tungsten carbide is tungsten alloys are very expensive. Or pure tungsten is also very expensive. So it has to have some applications, some key applications there. And all these have reasonable strength and also Young's modulus. Now, other important thing is when I'm designing, some cases I have high temperature application. I talked about that some high technical applications would be nickel super alloys in ceramics where you can use. Sometimes I have to design for impact, right? I'm designing a body armor. If I'm designing a body armor, what is the material of choice? What should we use? Any answers? You can type it in the box. So if I'm designing a body armor, what would you require? What is the property you would require? Just type your answers in the box, and then I'll read out if you have some suggestions. Light and strong. That is true. Impact strength, right? Impact strength. What do you mean by impact strength? Do you have any high fracture toughness, high tensile strength? I am designing a body armor. So if body armor's toughness, these are all right answers. So you need toughness, you need high fracture toughness, you need so primarily you need impact strength is the right word, because it has to absorb a lot of energy and it has to be lightweight, right? So what is the material of choice? If somebody asks you that I have to design a body armor which should take bullets, which can take high impact, what is the material of choice? What would you suggest? Can you give me a name of a material which would be something which you would recommend to take high impact strength? Kevlar is a very good answer. Kevlar, boron carbide has to be embedded somewhere. So boron carbide is very hard, but you need the matrix. So you will use a boron carbide polymer matrix. You will not use boron carbide as is, right? Because boron carbide again is very hard and brittle material. So you need to you use boron carbide as a strengthener. So boron carbide can be there. People use ceramics also, ceramic plates, multiple ceramic plates also, because that can take impact. And because there are multiple plates, there would be energy dissipation. If you, instead of taking one plate, you pack 5 plates there. So these 5 plates will have internal movement, and that can actually kill the impact. So the issue, what I'm trying to say is, you have to design for impact where energy can be taken by the material. So Kevlar can be one thing, boron carbide reinforced composites could be one thing, even alumina reinforced composites could be one of the solutions. So the property which actually explains or quantifies the impact is something called loss modulus. I don't know if all of you know about, heard of loss modulus. Anybody knew about loss modulus? What loss modulus means? So if you don't know what loss modulus means, loss modulus actually is a measure for how much energy gets dissipated. If I do a time dependent stress or time dependent strain, how much material how much energy you can dissipate. So the way, if you have a time dependent strain, it's typically given as epsilon is equal to epsilon dot, which is the amplitude, sine omega t. It's a time dependent strain you are giving, you're assuming it to be cyclic. And then stress, what happens is there is a delay in stress, sine omega t plus delta. So the strain and stress have a phase lag. And typically what happens is there is something called E dash, which is storage modulus, E dash sigma O divided by epsilon O cos delta, and there is something called E double dash. So storage modulus, and there is other term which is called these are so this is there is a complex thing where you have there are two kind of moduli are there, E dash and E double dash, and that is sigma O epsilon O. Just give me a second. E double prime is sigma naught by epsilon naught sine delta. So basically what you say is this tan delta actually represents the ratio of E dash divided by E double dash, which represents how much energy you will lose. And let me just give me a minute. I'll tell you the exact definitions of E dash and double dash. Just 1 second. So there is something called dynamic modulus, and this dynamic modulus E dash is basically storage modulus and E double dash is loss modulus. So there are two components, and the ratio tan delta, the ratio basically of loss and storage modulus, that defines how much damping is there in the material, how much internal damping is there in the material. So this ratio basically defines how much damping is in the material, internal damping. This internal damping basically quantifies that how much energy you will lose, because that's the energy getting damped in the system. So if I want high impact material, what I would need is very high loss coefficient, which is very high tan delta. And this tan delta, if you see, very high tan deltas are you see polymers have very high, elastomers have very high, rubber. So rubber is a very good damping material. So all the good dampers will have very good impact. But then in some cases you want also anti-piercing capabilities in body armor. So it's not only impact taking, but you also need some sort of a toughness and strength also. So that would be something like Kevlar. So you see Kevlar should be somewhere here. Let me see where Kevlar is. It should be polyester PMMA. You'll have to look for it. I'll look for it. But Kevlar also would have a very high impact strength, not as high as rubber, but then this also has strength. So rubber will be a very good damping material, but it will fail very fast. So wherever you need body armor application, you cannot use rubber, right? Because rubber will doesn't simply have that strength. It has very good loss modulus, but not the strength. So see, all the natural elastomers, butane rubber as very high elastomer. So wherever I need good damping property, I would use that kind of a rubber lining or something like that to design for impact. Okay, so these are some of the impact ideas. And to measure the impact, what you need is you need a ratio of storage modulus to loss modulus. So yes, so basically E double dash. So no, sorry, I've written up other way around. So E double dash, which is loss modulus, divided by storage modulus. So this actually is a measure of damping. This is a measure of damping, meaning energy loss. Okay. Now wear rate. Okay. Everybody understand what wear means? Can you reply what do you understand by wear? Some answers. So when I talk about wear, what do you mean by wear? Any answers? Coating, loss of material. Okay. These are right answers. So loss of material from, it can be tool to surface, loss of material or attrition, abrasion, attrition of, so basically losing material is something what is meant by wear. It's a very good answer. Loss of material is a very good answer. So why do we lose material? Do you have any possible physical reasons why material is lost? If I have two contacting surfaces, let's say it's a ball on a flat under some load W. This ball has H1 hardness, this surface has H2 hardness, and H2 is H1 is greater than H2. So my surface is a softer thing. Yeah, it's right. There are various mechanisms of wear. There can be abrasion is one thing. Abrasion is a physical scraping of the material when there is a physical removal of the material. But most of the wear doesn't happen because of physical wear. One of the key mechanisms of abrasion is something called adhesive wear. Right? If abrasive wear would be there, you know that if I don't know if you guys have gone to the villages, they actually put earthen pots. So near the, I don't know if anybody has seen that, but so back in the day, people would go to the wells to get their water, right? And they would use earthen pots. Earthen pot meaning basically pot made of clay, fired clay. And this earthen pot, that's what they would use for carrying their water. And they will place this earthen pot on a stone slab. And the stone slab will eventually wear out because of the contact with this earthen pot. And it was a very common thing you'd see. Or another example is, I don't know how many people have gone to the Dhobi Ghat, right? So in the Dhobi Ghat, the stone which they use for washing clothes, the stone wears out because of the micro impact of the cloth, and cloth is much softer, right? So what do you think is the mechanism in these kind of things? What is the mechanism of wear in these kind of, how does wear happen? What would be the mechanism of such kind of a wear where even softer material can, so usually the wear happens in the softer material, usually, but it can happen the other way around also, right? So when you write on the blackboard, right, chalk and blackboard, this is adhesive wear, right? It's a classic case of adhesive wear. But there is another case of adhesive wear where you write with a pencil on a paper, right? Which one is harder, the graphite or the graphite lead or the paper? If you measure the hardness.
Sir, graphite is harder, obviously.
Right, but then it wears out on paper, right? So that's a good answer. But so what I'm saying is the mechanism of wear can happen even with the harder material can wear also. That's what I wanted to give you the moral story. But some of the key aspects of wear is very simple. If I normally if I have if two bodies are in contact, wear would be a function of, let's say the contact is with under W load, and there is a contact in such a way that there's a sliding contact and we are traversing some length L, like I'm writing on a board with a chalk. Now the wear of the chalk will be functions of what? So where the volume of wear will be proportional to how hard I press the chalk, right? The load W. And it will also be proportional to how long I write, the length of writing. So my wear volume is proportional to W and proportional to L, W being the contact force. and it will be inversely proportional to the hardness of the chalk, which basically means your wear is equal to K W L by H. K is a proportionality constant. H is the hardness of the softer material. Usually, softer material wears. Usually, the harder material wear is a other kind of is slightly different kind of a phenomenon, which happens, but primarily the softer is the one which wears out. So, regardless of what the case is, the hardness of the softer material is inversely proportional. So basically, if I have my softer material is hardness is low, there will be a higher wear, right? So these are the concepts. So this is the wear coefficient right here.
Sir,
Yeah.
Sir, won't the wear be dependent on the hardness of both the materials?
No. So it will be a differential thing which will play a role, right?
Okay. So relative.
Softer material.
Okay.
If the softer material is softer, then it basically means that there is a differential is high, right? So the tendency to wear would be larger in the softer material, even though a little bit of wear will happen on the harder side also. Okay.
Okay, sir. Thank you.
Take a classic case of chalk on the board. Right. If I use chalk on the board, the longer I write, the chalk wears out. The harder I press, the chalk wears out. So it's a conclusive thing. So mostly, if I need, if I correlate hardness and wear rate, it's a no-brainer. The harder the material, the lower the wear rate. Diamond has the least wear. So you would see most of the things where you want to make a stylus for hardness measurement. It's made of all the profilometers are made of diamond. All the key things where you don't want wear would be made of diamond. Tools, very hard tools are made of diamond, and the usual suspects are diamonds and ceramics, which have very, very high hardness. Of course, high carbon steels are there, tool steels are there. Those are reasonably high, but then these are the things which have higher wear resistance. Okay. So I'll move to the next thing. So now when we talk about material selection, there are two key things. The first one is translation. So how do we identify the desired attribute for objectives and constraints? Because when I have to do material selection, I need to understand a couple of things. First thing which I would need to know would be function. What is this product which I'm designing doing? So function is the primary thing which we have to identify. Number one. Number two would be, then I have to formulate the problem in terms of objective. What is my objective? To minimize the mass, or so typically it's minimizing the mass, because whenever I actually design something, lower mass basically means cheaper for the most part. My cost goes down. So if I minimize, if I can get a function at lower mass, that would make my design economical. So then I'll have to have an objective function. That can be low mass, or there can be other things also. We'll talk about that. I'll give you some homeworks today that would give you other things as well. So that, but primarily it is trying to lower the cost, lower the mass, something like that. Some sort of a minimization or maximization issue. Then the third can be, you have to identify what are the constraints, subject to what condition this has to be done, constraints. And then fourth, I have to identify what are the free variables. Some constraints are imposed in my design, that this has to meet this. It has to have certain strength. It has to have certain stiffness, right? Those are the imposed conditions, because it has to have a function which determines that these conditions have to be met. Other than that, I have some free variables. I can make it fat. I can make it slim. So those could be some geometrical parameters, will be free variables which I have, which I can play with. Right. So I'll have some free variables. So these will be the function and objective and constraint. So these would be some sort of these. We have to translate an attribute. So that this is part of translation. All these are part of translation, these four things. Then after translation, what we have to do is we have to do screening and ranking. Then we identify a whole bunch of materials which may meet our design, which may be useful for us, but then we have to rank it on conditions. So how do we rank it? We can rank, so material attributes can be based on, it can be based on cost, environmental thing, thermal behavior, physical behavior, mechanical behavior. So we'll have to figure out a way to local availability in some cases, whether I have to import that material, can I source it locally? So all these things would basically help to rank the options which I have based on certain things: cost, availability, whether it's getting imported, whether it's environmental friendly. So all these attributes would be there, with which we will basically screen and rank our materials. That's very important in design. That a lot of things can meet our goal, but then we have to make an educated decision. How do we come to the thing which we have decided? So basically, translation basically means function, objectives, essential conditions to be met, which is constraints, and free variables, from which we do screening criteria. We get a numerical value limits on the property values, and then we create a criteria to rank the material. So that's how you basically do material selection. This is primarily for material selection. This is not a overall design idea. It's just a material selection in design. Overall design we have discussed in the introduction class, right? This is only for material selection, right? So let me give you an example. What do I mean by all this? First thing is, say, screening on attributes if I have to do. So basically I have to make a heat exchanger tube, right? And the requirement is that it should operate at 100 degrees centigrade, be electrical insulator, and be good thermal conductivity, should have good thermal conductivity. So these three are the requirements. So how do I go ahead and choose it? So I'll basically look for materials which can operate above 100 degrees centigrade, those who have high thermal resistivity, electrical resistivity, and those who have high thermal conductivity. So go ahead, use this parameter, and then list a whole bunch of materials which meet these criteria, right? And then go ahead and select the one which you feel that would be right thing, but they should meet these. So from the requirement, you translated it to some quantitative data now you have, right? And then there can be some things where you want a cheap metal window frame, right? So cheap window frame are the ones which are extrudable. Aluminum extrusions are cheap and they meet the job. So you will basically say we would use materials which can be extruded. So extruded materials typically are softer materials. So aluminum, brass, these will be extruded, but then you choose the cheaper one, because steels typically are difficult to extrude. Not that you don't get extrusions, you get extrusions in steels also, but you can get very nice shapes in aluminum where you will get reasonable amount of stiffness at a much lower price. So they will actually have these nice sections, extruded sections, which are reasonably stiff. Okay, so that's how you can actually screen on links also. So that's how you can basically get. So you can both screen on attributes and links. The screening attributes can be, you need to compare the material properties and the elastic limits. So there are like 4 options. You see, look at ceramics, look at metals, look at polymers, and look at composites. So these are, so you can basically, you can have these charts which you can make the decisions from. And then you can rank by performance. So performance can be cost per unit strength, mass per unit bending stiffness, volume per energy absorbed. I'll give you an example. So these are, I'm giving you some metrics. I'll actually derive a few things today and show you how do you come up with. I gave you some example in the previous time for a very simple condition. I'll take slightly more complex condition. This we had discussed in the last class, right? For tie rod. I'll take a little more complicated condition where I have a stiff panel. So basically what happens is I have a panel. Everybody understands what a panel is? What do I mean by panel? You can type it in the chat box, and then we can. How do you say this is a panel? What would be the key requirement of a panel? Thin surface is one answer. Thin board is one answer. Yes. So I think that's the people are now getting it. So you'll basically have two dimensions reasonably large, and one, the thickness will be very small, like glass panel, your window panel. So panel basically means two dimensions. You can have, sorry. So you can have length, and B is say, so this is length and this is breadth. And thickness will be much smaller than these. That's why it's called panel. Now, I want that my stiffness of this panel, sorry, the stiffness of my panel should be S star. My stiffness of panel should be greater than. Stiffness of panel should be greater than some design stiffness S star. That's my one of the constraints. So let me just list out what we are trying to do here. I want to make a stiff panel. So that's one of the constraints. So basically, first thing is the function. So function, if you go, let me just go back. Function is, it's a panel. Objective function, it is a panel. It is a panel. Second thing would be that objective is to minimize the mass. Minimize the mass. Right? That's what I want to do. I want to make a stiff panel. And third will be constraints. So constraints will be that stiffness should be greater than or equal to some S star, some required stiffness value. That's one thing, right? And then the other thing will be, it has to have some length, it has to have some breadth. So these will be, this is a functional constraint S star, and L and B are geometric constraints. So there are two kinds of constraints. One would be the functional constraint, and these L and B are geometric constraints. Now, what is the free variable which I have? So fourth thing is free variable. Now, what free variable do I have at my disposal? Yeah, type in the chat box what free variables we have here. Thickness, very good. H, thickness. What else? Material, very good. So thickness and material are the two things which we have at our disposal. These will be free variables, right? Now, how do I define a stiffness? How do I define a stiffness for a panel? How do I compute that stiffness? How do I quantify stiffness? If I were to quantify stiffness, how do I do that? EI. That's a good way to look at it. But it's not only EI, right? So let me just say it's a function of EI. You're correct, but there will be some other geometric parameter also which would come into there, if you remember from your mechanics of solids. So let me just actually show it here. So basically, what happens is I have. Let's say I am doing a simple cantilever I have. So if I know the deflection in cantilever is a function of what? It is a function of load P LQ over 3I. If you remember that in this kind of a configuration. In this kind of a configuration, simply supported, In simply supported beam where there is center loading, it is delta is equal to PL cube over 48 EI, if you remember that. These I remember, you can derive it if you feel like, but we'll not go there. So in a nutshell, I can say delta is proportional to L cube over 3 EI. L cube over 3 EI, right? And sorry. Delta is proportional to P L cube over EI. This is what I wanted to say. And P is equal to stiffness times delta, right? So P by delta will be stiffness. So P by delta is equal to stiffness is equal to if I have some proportionately constant C1 EI over L cube, where C1 is some constant depending upon this C1 constant depends upon my loading conditions, loading and support conditions. This C1 will depend upon loading and support conditions. Agreed? So I know that my S star so my C2, if you see C2, so my C2 EI, actually let's say C1 here, C2 I'll use for someplace else. Oh, sorry. Let me go back. So if I want to do that, I will say C1 EI L cube. So basically my this term C1 EI over L cube should be greater than or equal to S star. Everybody agrees to this? S star is the minimum which is required by functionality. So now this will be my one of the constraints. This is one of the constraints. And L and B are also constraints. I need a certain length of the panel, certain width of the panel, right? And my objective function is to minimize the mass. Minimize mass. So mass is nothing but density times rho times L times B times H is equal to mass, right? This is what it is, and this is what I have to minimize, but subject to this, right? Now L is capital, which I mean, so I'll just keep it capital here, right? Now let me just simplify this. So this is the constraint. Let me rewrite the constraint, and this is what I have to minimize. Let me go ahead and erase all this. So that I can write, and I'll write only two things now. So I have C1 EI by L cube is greater than or equal to S star. This is the one equation which I have. I, we know that I is a function of, it will be BH cube by 12 you have L cube times E should be greater than or equal to S star. And what I have here is I have M is equal to rho B capital L H, right? So what I can do is, if I have to understand, plug in the H cube from here. So what is C1E B divided by 12 L cube, just plug the H value, will be M divided by rho divided by B divided by L cube less than equal to S star, right? I can go ahead and do some jugglery here and find out what will be the mass should be greater than, if I do that, I said M cube is equal to S star times 12 L cube, S star times 12 L cube, rho cube, B cube, L cube divided by C1, E and B. So let me just do this. M cube should be greater than or equal to, my mistake, should be greater than or equal to like this. So M would be, if I go ahead and do this, M is greater than or equal to, what do you get? Some constants, this raised to 1 over 3. This raised to 1 over 3. So this is, if I want to get the material parameters, it will be rho divided by e to the power 1 by 3. And other parameters, I'll just put the material. So this is the material index right here. And everything else I'll just plug in here. You'll get S star 12 L cube, 12 L6, B cube, C1, B, right? So this you can go and simplify, but my interest is this thing. So my mass, to minimize my mass, I have to minimize this term, rho divided by e to the 1 by 3, or maximize e 1 by 3 rho. So this is my material index, which is of interest to me. This is the material index. This is the material index. This is a material index of interest. Let me go back to your formulation. This is the formulation. Sorry. This is what the formulation looks like. I have to have, this is the material property which I have to worry about. Rho divided by 1 by 3. So I have to maximize E1 by 3 rho. This is the material parameter. For strength, it will be sigma y 1 by 2 by rho. I'll show one example for strength also. I'll take one example for strength as well today. But trust me, if you do this, you'll get this for strength. You'll design it for certain required force. It has to take certain force. And in that case, you, instead of minimizing the mass, you minimize the mass, but subject to not stiffness, but certain amount of force. I'll show you how to get that as well. So these are some of the things which I wanted to show you. Another example I'll show you where you have a light stiff beam. So here you saw that this is not simply rho over E, right? So I showed you that this is for stiff panel, you have 1 by 3. For just rod in tension, you have E by rho for one-dimensional loading. It is E by rho. For a light stiff panel, you have E1 by 3 rho. For light stiff beam, you have E1 by 2 by rho. This also I'll show you. This is also very similar stuff you have to do here. So what we can do is, again, same kind of a thing. Stiffness, your C2 times EIL cube should be greater than or should be greater than or equal to S star. Right here, what happens is it's a beam and a cross section is square. So here the cross section is square, is a square. That's the constraint. So I'll just read out what are the constraints here. Here again, the function is a beam. You have a beam. The objective is to minimize m of the not panel but m of the beam. I'll fix it in the minimize the mass of the beam. Constraint says it's a functional constraint. Let me go back. Functional constraint, which is the bending stiffness should be at least S star. And then the other geometric constraint is that the cross section should be a square. So these are the constraints. Free variables are cross sectional area A and the material. So that's all you have in your. These are things which you have for your constraints. And A and M are the free variables. So how do you go about doing this? In this case, what you got to do is you have C2 EI by L cube. Now what happens is I is A square by 12, B4 by 12, which is A square by 12. I'll just use A as one of the things. And M is rho. M is equal to rho A L. Right? That's the mass. And then what I have to do, the free variable which I have here is this cross-sectional area A. Right? So if I have to do, I do C2 E, I is A square by 12 L cube is greater than equal to S star. Then I have C2 E A square is M square by rho square L square by 12 L cube should be greater than equal to S star. Right. Again, what you do is M square is greater than or equal to S star L to the power 5, I believe. L to the power 5. Sorry, my mistake. L to the power 5 and L to the power 5 rho square L to the rho square 12 divided by C2E. Now what we will get is M should be greater than some parameter here. I'll not, you can do the math. And then this would be rho E1 by 2. This has to be for minimum mass, this has to be minimized or the inverse has to be maximized. E1 by 2 rho has to be maximized for stiffness. So these are the parameters where so in different conditions, you will get different material parameters. E by rho, E1 by 3 rho, E1 by 2 rho, or sigma y 2 by 3 by rho. So these will be your material indices which will govern what you need. So instead of, so these are the parameters I have to minimize. These will be my physical material parameters which I have to maximize or minimize in my function. So I'll also do one case for this thing for your strength, just to showcase that material. So if for strength, what do you mean is you need, I'll just say objective function will be, in this case objective function would be, I have to have F star, which is the force. It has to bear some load, right? So basically it has to bear some load. So in that case, what will happen is my objective function is to bear some load F star, and constraints again would be same. Constraints would be square cross section and the objective function is minimize mass. Minimize mass. Functional constraint is it should be able to take F star load in bending. Let's say, so it should be able to take this F star bending load. Okay. So in this case, what I would say is sigma y is equal to my by I. If you remember these formulas, this simple bending formula. So that basically means F star times L times B by 2, y maximum y will be B by 2 divided by B4 by 12, BH cube by 12. So both is BB. The depth is also B, and the both the dimensions of the cross section are, so the width and the thickness, height, both are BB. So B4 by 12 is this. So basically, and we want that, so if we do this, F star should be less than or equal to sigma y B4 by 12 2b 1 over L. Just do the so this is the constraint which I have, right? And I know m is equal to B square L rho. That is m. So if I go ahead and plug, my F star would come to sigma y times m by L rho 3 by 2 into 1 over 6L. Just go ahead and do this. So basically what you will get is m is greater than or equal to some constant C dash times rho divided by sigma y 2 by 3. Rho divided by sigma y. So if you do this, this is what you will get. Rho divided by sigma y raised to 2 by 3. Sigma y raised to 2 by 3. So I'm just giving you a quick overview. Simple. This I will give something like this. I'll give in the homework. So you'll do quite a bit of this. So you should be fine. So this is what I wanted to show you. This is what it is here for strength. So for strength, the parameter is different. For stiffness, the parameter is different. So I just wanted to derive one for strength for you. So this is what I derived the strength one for you. Sigma y raised to 2 by 3. I'll stop here a little bit. If you have any questions, ask me, and then we'll go ahead and continue the remainder portion. Few more slides to go. Before I move on to the next thing. Either you can type in the chat box or you can unmute yourself and talk to me. Both ways is fine.
So will it be given?
What will be given?
Stiffness or strength?
No. You will use the charts. Your charts will be, when I give you a problem, even in exam, right? I'll give you the charts. And in the homework, what I will do is I will actually give you links. All these charts are free on the web. In Ashby's book. These are called Ashby's chart. This is a design methodology. Material selection methodology is very popular. This Ashby's material selection methodology is a very popular methodology for material selection. And all these things are available online. I'll give you a link for Ashby's chart so that you can actually see it at your screen and choose the right material. Of course, these are also here, but they may not be very legible for you, right? So they may not be very legible. So what I will do is I'll actually send you the links for all the thing is in open. It's all open source. Every information, Ashby's chart, all the data is there, and I'll send you the link for that data. When I do the homework, I'll send you the link as well. So all this data will be there with you. You cannot design anything without the data, right? That you have to have access to. Any other questions? So if not, what I will do is I'll let me finish it and then I'll give you another opportunity to discuss. Okay. So this is Ashby's methodology. This is actually whatever I was teaching. This is one slide says all. right? So you first need to identify what is the function. Are you trying to make a mirror? Are you trying to design a table? Are you trying to design a lathe? So function you need to know, or what is the function? Is it a structure? What is it? So function you have to have very clear thing in your mind. Okay. Then you have to have an objective. What do you want? Minimum cost, minimum weight, maximum energy storage, minimum environmental impact. These objectives you have to clearly define. And then come up with constraints. Stiffness specified, strength specified, fatigue limit, geometry. So all these constraints you will have to come. And then come up with an index. In your case, we showed you some various indices, right? We showed you indices both for strength and stiffnesses. Strength and stiffnesses. We took 3 examples, right? One for tie rod in tension, the other one panel, number 2 panel, number 1 tie rod, and number 3 beam. So 3 distinct examples I took, and then find out the material index and then minimize or maximize whatever is required. Sigma y by rho maximize, rho by sigma y minimize. Okay, so there is something called material indices. The physicists view material differently. They will see cost, they will see density, they will see modulus, they will see yield strength, endurance limits, thermal conductivity, commutative thermal expansion. That's a physicist's view of material. The engineer's view of material is very different. He will see things as these stiffness to weight ratio, right? So, or fractional of whether it is tension, whether it is bending in beam or panel, all those will have different stiffnesses. The stiffnesses will be a function of density. Like I want to do stiffness per unit mass. I want maximum value for my maximum bang for my buck, which basically means with minimum mass I should get maximum stiffness. So that's what engineers say, do rho by E minimization, not E, but rho by E. Right, that's the best value. For strength, it is rho by sigma y. So everything is normalized with respect to the density, which meaning I'll get the property. So it's basically a metric which actually shows that I get per unit mass, I get the maximum either strength or stiffness. That's what basically it means in an engineer's parlance. So we just don't worry about absolute E, but E by rho. Right, because if I maximize E by rho, meaning I am getting maximum stiffness in lightest material. You get me? So that's the engineer's perspective. Okay. And then you can do chart selection. This I have talked about a little bit. You figure out what you want to, what is the minimum you want, rho by sigma y, and all these materials are your candidates. So these are not candidate, and these are candidate. And then you use your screening criteria to figure out what you want out of those. Okay, but that's how you decide to split the thing, acceptable, unacceptable. Okay. So all materials basically you screen on property, material indices. Now you have, I showed you, get a subset of materials, get supporting information, identify prime candidates, use local conditions, and then final you have a material choice. So it's a methodology which you use to identify the right thing. Even though there is something better, but I have to import from China, I'll rather source it here, even if I have to make some compromises. So these also are inherent part of design. Local conditions, environmental conditions, these are also inherent part of design. You cannot decouple from it. Okay. Then there is material shapes. So when you choose some designs, right, you should also have in mind, if I'm choosing this material, if I'm choosing plastic, right? If I'm choosing plastic, means that the part has to be probably injection molded. If it is a big part, it probably has to be compression molded. So I also need to have an idea how am I going to make that part, right? Just designing doesn't mean that your job is over. Design should also have an end goal in mind. I'm designing something, whether it is manufacturable or not. How do I manufacture it? I'm using this material. This material, how would it be manufactured? So you need to have some sense. The moment you choose the material, right, you are tying to a manufacturing process. If I'm choosing polymer, I am tying to some sort of a molding, primarily injection molding. And if it's a bigger piece, compression molding. If I am tying to metals, then I have a lot of choices. With metals, I have machining, I have casting, I have forging. Lot of choices I have with metals. But if I say choose CFRP, then I am limited. There are only very few processes which I can do. Vacuum resin transfer molding, or some sort of a compression molding, or hand layup. Very few processes are there for manufacturing composites. Right. So depending upon what material choice you have made, you also have tied with the manufacturing process and what shapes you can get. The material actually constrains you in what process you can use and what shapes you can create. Right. So that understanding also you should have. And then you should also know about something process material compatibility. So if you see what things can be cast, what things can be molded, what things can be deformed. So all these class of materials, right? You have various class of materials like ferrous material, refractory material. So metals are there, ceramics are there, polymers are there, composites are there. What all can you do to the composites? For composites, you cannot do casting for composites, right? Casting is all 0, 0, 0. I can probably do metal matrix composite, I can cast, but polymer matrix I cannot cast. Right. So the moment I choose a material, I also have chosen the shapes and the processes it can be done. So you need to have some idea of I choose this material, but I should have in the back, can I create that shape? And what process will I use? So that ties you. So the moment you choose a material, process and shapes also have some limits. You have some limitations of processes and shape, and you need to have some appreciation of manufacturing also as a designer. And then these are also some what kind of materials, what processes can you do? Like sand casting, you can do metals, you can do non-ferrous metals, but ceramics, glasses, elastomers, thermoplastics, thermosets, polymer foam, composites, these cannot be sand cast, right? Say, take the example of machining, conventional machining. Conventional machining, you can probably do a lot of things. You can do metals, you can do non-ferrous metals, you can do ceramic. Ceramic, you cannot do probably freeform machining, but grinding you can do in ceramics, right? So some sort of machining can be done. Drilling can be done. Elastomers, plastics also you can machine a little bit. Composites also you can drill. So machining is one of the more flexible processes. Of course, adhesive you can do everything. So that way you have to figure out what will be the process to create the shape which you want. So once you identify the material, process and shape, this appreciation you should have. Okay. And then again, similar kind of things. What processes, what shapes can be created in what process? Let's sand casting, right? I can create any shape, right? Machining and create any shape. But there are some processes, let's say extrusion. I can create some shapes in extrusion. All the shapes are not possible when I do extrusion. Let's see what they say here for extrusion. Actually, they have no extrusion here. So what they have is, yeah, extrusion they have. So extrusion, I can create circular, non-circular shapes. That's it. I cannot create free-form shapes in extrusion. Right? Whatever I can make a long thing with either circular cross-section or non-circular cross-section, but it will be just a long product in extrusion. And then you can do selection by technical analysis. You can do multiple constraints. You can have density, modulus, sigma, V. So you can do a multi-objective optimization, some analysis you can do. And then I described about the process material relationship is because the moment you have material, you are tied up with both process and shape. You can do some similarity based selection. Go ahead. So basically find a material that is X or like product Z. So you can use some idea of similarity. So you basically, if there's some existing product out there, you can find a material which is similar to the existing product. And then there is something very interesting where what you can do is there is something called Pareto frontier optimization. Some people would have heard of it, Pareto frontier optimization, which basically means it's a multi-objective. So you have two parameters which you have to optimize, say cost, you have to minimize the cost and maximize the performance. So this front would be where you have solutions. So you can use, depending upon what weightage you give, If you give weightage to cost, you'll be here. If you give weightage to performance, you'll be here. So depending upon what weightages you give, you can get a solution. But the solution is the front. This front is your solution. It's called Pareto frontier. This is a traditional way to optimize cost. You just plot it, do a scatter plot between cost and performance, and take the frontier solution. That would give you optimal solution, and based on weightages, what weight we give, whether you want to give weight for performance index, so whether you want to minimize the cost or you want to maximize the performance, you choose accordingly. 50-50 will be here. Cost will be here. Cost will be here. Equal weightage will be here. Performance will be here. Performance centric, performance, you are biasing in terms of performance, you'll be there. Okay. And then this is what I just explained to you. This is what is multi-resource optimization. So this is one real example how people have done it. So it is for refrigerator insulation. You can use aerated concrete. You can use lightweight concrete. You can use foam. You can use cork. Right. So these are all the solutions, trade-off surfaces. Now, depending upon what you want to use, you could pick one of those. So basically, that's how you go ahead and pick the solution. So this front will be your solution. Okay. Let me summarize it. I talked about engineering materials here, material property charts, gave you a concept of material indices, and then basically came up with the material selection methodology by Ashby, which is a very good way to identify what material you want to use, and gave you some engineer's perspective, not physicist perspective of material. And then I talked a little bit about something called multi-objective optimization, which you will choose when you are doing a real life design problem. So this is where we stop. And now I'll take questions for 10-15 minutes. Let's have some discussion. And then next class, we'll start fatigue. Okay. So I open the floor now for questions. Now you have to talk. I'm done with the main content of course today. Okay. Feel free to ask anything you have in mind now. Either you can type in the chat box or you can talk to me. No questions? Whatever we discussed today, do you have any questions, any concerns, any issues with it?
Sir, can you please explain slide 69?
Slide 69. Okay, this one, Pareto frontier, right?
Yes, sir.
Okay, let me actually go ahead and explain this. So now what I have to optimize two things, say cost and performance matrix, right? So what I will do is I will draw a scatter plot for every solution, right? I have for every solution I have a cost and I have a performance index, right? I can plot this. I can do a scatter plot. Agree? Right? Now I have this scatter plot. What do you think will be an optimal solution? Should I choose this? What is my goal here? My goal is to minimize the cost, right? And get the maximum best performance. Minimize cost and maximize performance, right? These are my two goals. Yes or no?
Yes, sir.
Yeah. So how do I get maximum performance? By maximum performance, I want to be as high as possible, right? I want to be here, right? Minimize cost means what? What will happen is I want to be as low as here, right? So basically, let me understand. Let me try to understand. To understand. So basically, my performance indices are high on this side, low on this side, right? This is high to low. This is the other way around, right? Because this is what I want. I want high performance, and then I want cheap, low price, and this is expensive. So I make the chart. So this is cheap. The bottom one is cheap, and the bottom one is cheap, because cheap is my desirable. This is my desirable, and high performance index is desirable. So basically I want minimum cost and maximum performance. So now what I want to do is I would like to be here and here, right? I would like to be closest in performance to high and lowest cost. So where will this solution occur? The solution will occur on the front. This front. This front signifies this is the maximum. This is the maximum performance index. So if I need maximum performance, if I don't care about the cost, right? What should I choose, right? I should choose something that is, say, here, right? I'm not worried about the cost. But if I'm worried about the cost, I'm compromising on some quality, but I'm getting at a minimum cost, right? This is, if I say this is more expensive, right? This is, if I take X and Y, which one is more expensive? Y is more expensive than X. So I choose X, which is slightly inferior in performance, but lower cost. So what basically it means is this front would give you the lowest cost barrier and the highest performance thing. Both it will give. So this is the optimal parameter. Now I can have combinations of my requirement. I can have weighing parameters. If I put lot of weightage to cost, right? I can compromise on quality on the performance index. I go here. If I have to worry less about the cost, I will go here. But a combination, if I want to give both equal weightage, I'll be here. So this is called a Pareto front, because this gives me optimal solutions in respect to price and performance both. So this is where I have an optimal front. So what I can do is, depending upon what weightage I give, if I give weightage to the cost, I will be here. If I give weightage to the performance, I'll be here. But nevertheless, all the solutions will lie on this front. All my desired solutions will lie on the front. Is it clear or no?
Yes, sir.
So that is what Pareto frontier means. If you have two things which you require, your solutions would lie on the front. Now you can choose based on what is important for you, whether it is price or performance. If you want performance, go up. If you want price, go down on that front only. If you want a weightage 50-50, you be in the middle. But regardless, your solution will be on the front, on the Pareto front. Please explain what is meant by index in different scenarios, right? So, okay, that's a. Let me go. What I will do is I will just do this. I think I had this, right? So we. Okay. So basically, if I have tension, right? If I have tension, my stiffness to weight ratio, the stiffness to weight ratio is just given by rho over E. For minimum mass, if I want to minimize mass, if I maximize E over rho or minimize this or minimize rho over E, I am fine for tension. But for bending, that is not the case. For beam bending, I don't have to minimize rho over E, but rho over E raised to 1/2. I showed you, I derived for it, right? I derived for it. So in tension, rho over E works fine. But the moment I come to bending, I'm bending it, right? In bending stiffness. In bending a stiffness, it's not rho over E, but rho over E to the power 1/2, as I showed you here I'll go back and I'll show you what I mean by rho over E by 2. I actually derived it for you. So if you remember, this. So this is for light stiff beam. So there, sorry. So this is for one dimensional. This is for light stiff panel. This is for keep. Okay, so I'll just go back. Okay. So this is for beam, right? So for beam, you see that your stiffness comes not from E by rho as in tension. Your stiffness comes from E1 by 2 rho, and I showed you how it comes, right? I derived it right here. So basically, for different conditions, you will have different material parameter. For tension, it is E by rho. For bending, it is E1 by 2 rho. For panel bending, it is E1 by 3 rho. Let's say panel, light stiff panel. Yes, E1 by 3 rho, right? So do you understand what I mean to say? That this material parameter is different, same. Stiffness to, you want maximum stiffness at minimum. So you want minimum weight and maximum stiffness. But the indices which you have to identify for stiffness to weight ratio is different in different configurations. That's what I wanted to say. Okay.